blockchains are sort of the latest kid on the buzzword block. It's climbing the hype curve to me incredibly quickly, and the top is yet to be seen. You talk to somebody in the financial industry. I was at a dinner party and talking to somebody, and he turned out to be a banker. And I asked him if he'd ever heard of blockchain, and he said, "Of course, it's a game changer, a potential game changer. Everybody in the financial industry knows or is looking into blockchains." So I looked into blockchains, and I couldn't find a nice, coherent description of what it is. They're you can get very technical descriptions. You can get a lot of hype. This is how it's used, and so on. Uh, so I thought I'd take a shot at trying to characterize a blockchain. So, to my mind, there are three elements, and I'll go through these. One is a contract. Uh, the Could be more than one. Could be a coherent collection of contracts. Doesn't much matter. Uh, but anyway, they're related. And then, given a contract, you have transactions within the contract. And the second element of a blockchain is an immutable history of transactions within the contract. And so immutable means it can't ever be changed. Uh, and then the third, and this is what really twisted my mind around, were the cryptographic aspects of it. So you encode the contract, and then you can prove assertions about compliance with the contract, and you can verify those proofs. And the proof in this sense means mathematically correct from a cryptographic point of view. So what do I mean in more detail by a contract? Essentially, it's a specification of how individuals or entities interact with the blockchain and what are their obligations and rewards from this interaction. So it's much more like a programming language contract than it is like a legal contract. Um, I guess you could make them legally binding. Uh, the trouble with making them legally binding if they cross jurisdictions is who's in charge. Um, but in any case, it is very similar to a contract. And the contracts can be either explicit or implicit. So you can lay out in some formal programming language uh, the contract, or you can build it into the code. Uh, and they could be hard coded, which tends to mean, well, doesn't necessarily mean they're implicit, uh, or programmable. So Bitcoin is the example that people have heard of mostly, uh, and that's hard coded into the contract, into the into the platform, and it's implicit. It's hard to find a good description of what the Bitcoin contract is. You see some discussion of miners and consensus and so on, but it's hard to find a good description. So I call it implicit. There's something called zero cash, which is hard coded into the platform, but that's explicit. There's a technical paper you can find that gives you all the algorithms you need to know about how zero cash works. Uh, and then there's Ethereum is another platform, and that's programmable, and it has what it calls smart contracts. So a smart contract is a program. There are some portions of Ethereum that are implicit, things like taxes and so on, and the rest are defined by the program that you write. Okay, and this is a Turing complete program, so you can write anything you want. You keep a history of the blockchain. So it's an immutable public ledger, and this is what some people focus on, is that I have a history of all the transactions and I can view this as a distributed database, and that's true. And then the contract tells how you interact with the database. You get a set of transactions against the contract. If a transaction is valid, then it goes into a blockchain. It gets distributed. There are mechanisms to encourage a distribution in various platforms. But it's replicated. So from a reliability point of view, there's you can get a copy of it from a a non-repudiation point of view, this is immutable, and so immutable is a big word. It means it can't be changed. Well, how do they do that? Well, they hash it. So if you take a hash of a value, then the value can't be changed without changing the hash value. And you can argue about kinds of hashes and so on, but at least in concept. So a second part is this distributed public ledger. And then the third part is the cryptography, and this is the thing that just twisted my mind all around. I have never seen such complicated algorithms. But fundamentally, you put the contract, or you code the contract. It could be hard-coded. So anyway, you go into a key generator, and this key generator uses large prime numbers to generate a prover key and a verifier key. And the only thing in this whole process that is kept secret, and has to be kept secret, are these large prime numbers. You know, it's based on the idea that some problems are computationally extremely difficult, and one of the challenges of theoretical computer science for the last, since Steve Cook started this in 1971 or 2, is to see if things called NP are the same as things called P. And no one can prove it, but everybody agrees they're not, that NP is really hard. And so the key generator is based on prime numbers and number theory, and out comes a prover key and a verifier key. So the prover key lets you, as a participant in this contract, lets you assert that I have complied with the elements of this contract, at least the ones that are under my control. And so you just make that assertion. You encode that assertion in the prover key, using the prover key, and you get a compliance token. Okay, so this is, I mean, if this is confusing, think of public key and private key. Okay, so this is not a private key because it's public, the prover key is public, but it is an encoding of the assertion that you've complied with everything. And if you're a verifier, you look at this compliance token, you use the verifier key, and you can prove that you can determine that the prover in fact has complied with all the elements of the contract under his control or her control, or has not. Okay, so the interesting thing is that everything is public except the internals of the key generator, and in particular the random numbers, the big primes that you use. You might get slightly different pictures if you have different theoretical bases. So it might be that there's more than the prover key that comes out of the key generator. There's a third thing. This is based on something called the quadratic span programs, which again is a technical paper that you could look up. One of the interesting things is that you can keep secret all of the details of what the prover is proving. So the prover says that I have complied with all the elements, but it doesn't tell you what the elements are. You can keep secret who the prover is. You can keep secret, say it's a financial transaction, about who is paying what to whom. That's all encoded, and you can determine if it's true or not. But you can't get any details, and there are things called zero knowledge proofs. And if that's confusing to you, welcome to the club. There's a very nice blog post by Matthew Green called something like Zero Knowledge Proofs Illustrated that explains it in at least it was accessible to me, so in reasonable terms. You know, and there may be elements of the contract that are outside the prover's control. So there are consensus processes that say that in essence keep you from double spending. So some of the variants of blockchains, some blockchains are public, some are private. So you can put it on the internet so anyone can have it, or you can put it on an intranet so only your organization can have it. Private blockchains will be available to stakeholders. There's on-chain and off-chain. So in some blockchains, all computations are on the chain. So in Ethereum, for example, it's all You program in a Turing-complete language, so you could do everything you want, and it becomes a portion of the history. On others, you would move some computations off-chain. And at the moment, blockchains are strictly experimental. Uh, as times goes by, the systems that use blockchains are going to get bigger and bigger. And at least to my mind, the notion of keeping everything on the chain is going to prove to be too cumbersome, and so there will be a lot more off-chain. So as a software architect, that becomes interesting. Then you get a question of what do you put on chain, what do you put off chain, and it raises some interesting issues. But for the purposes of this talk, is just, there is on chain, there's off chain. The fact that things are public doesn't necessarily mean that everybody has permission. So some blockchains require permissions to access them, others do not. Okay, so that's it. I mean, if this was successful in helping you understand blockchains, then I'm grateful. It helped me understand it to write it down. So that's the end.